This is the last class of this semester, and I would like to make an announcement for the final exam. The final exam will be next Wednesday, it's December 13, from 11 a.m. to 1 p.m. It's a 2-hour exam. Therefore, you can prepare but it's final, so 3 pages of cheating sheet. So you need to prepare 3 pages of cheating sheets, and the final exam covers from beginning to end. So final exam covers from the beginning to the end until whatever I'm going to cover today. So we have been looking into the partial differential equation up to the first order, and today we are going to study the classifications of partial differential equation for the second order. So the title of my lecture today is classification of the second order partial differential equations. In order to pursue this goal, I would like to introduce the following notations. For example, Zx as partial x partial z, Zy is partial y partial z, Zxx is partial x square partial square z, Zxy is partial x partial y partial square z, Zyy is partial y square partial square z. And the general second order equation will be of the following form. PDE will be of the following form: AZXX plus BZXY plus ZYY FXY Z ZX ZY. So we are considering two independent variables. Independent variables x and y, and a xyz, bxyz, cxyz are continuous functions of x, y, z. Briefly, we have covered the condition for the continuity in last class, but if I repeat that, so a function f of x is called continuous at x0 if there are small numbers epsilon and delta greater than 0, such that fx minus fx0 is less than epsilon for x minus x0 is less than delta. The classification is as follows. Classification of second order PDE. If p squared minus 4ac is greater than 0, it's called hyperbolic type. p squared minus 4ac is less than equal to 0, it's called parabolic. p squared minus 4ac is less than 0, it's called elliptic type. So we are going to consider 3 different types of partial differential equations depending on this classification. Sometimes it is more convenient to use the function uxy and the vxy and write down and express cxy as z uxy vxy. And the merit of this approach is going to be seen quite soon. But then we need to express the partial derivatives in terms of u and v. For example, zx is, using chain rule, you can say z partial x partial u plus partial v partial z partial x partial v. You can write it down as zu ux plus z3 vx. Likewise, zy is partial u partial z partial y partial u plus partial v partial z partial y partial v, which is zu uy z3 vy. Then zxx can be written as the following. This is actually zu ux z3 vx and x. So you can write down as z ux plus zu and uxx and z3x plus z3 vxx. And if you take a partial derivative of zu by x, you got the following expression. That is zu ux plus zu 3x and ux, right? Plus zu uxx plus likewise z3 ux plus z3 vx and vx plus z3 vxx, right? And probably I need to make a copy of this. Copy and delete. And next page, I just need to paste it. move it. And if we continue that, we have the following expressions, which is equal to z u u and ux square plus z u v ux vx plus z u ux x plus z v u ux vx plus z v v vx square plus z v vxx. And so that is z u ux square twice of z u v ux vx plus z v v vx square z u ux x z v vxx. And likewise, we can get the same expression for zyy. Likewise, zyy is equal to zuu uy square twice of z uv uy vy z vv vy square plus cu uyy z v vyy. How about zxy? So zxy is actually zx, and you can take a partial derivative y after that. So that is more like zu ux z v vx and to the y, and that. So I'll just start with that. Zu ux z v vx to the y is same as zu y ux plus zu uxy plus z v y vx plus z v vxy. So you can say zu uy zu v vy ux plus zu uxy plus z v u uy z v vy and vx plus z v vxy. So if you write down, that is z u x uy z u v vy ux plus z u uxy plus z v u uy vx plus z v vy vx plus z v vxy. So you can write down z u ux uy plus z u v ux vy uy vx plus z v vx vy plus z u uxy z v vxy. Then azxx plus bzxy plus c z, y, y. You can write down a with z, u, ux square plus twice of z, u, v, ux, vx, z, v, vx square plus zu, uxx, z, vxx plus p z, ux, uy, z, uv, ux, vy plus uy, vx plus z, vv, vx, vy plus zu, uxy, zv, vxy plus c, zu, uy square twice of zuv, uy, vy plus zvv, vy square plus zu, uyy plus zv, vyy. Okay, so let's put them together. A ux square plus p ux uy plus c uy square c uu plus 2a ux vx plus p ux vy uy vx plus 2c uy vy z uv plus a vx square plus p vx vy c vy square z vv plus auxx plus puxy plus cuyy cu plus avxx plus p vxy cvyy cv. Let's say this is alpha, this is beta, this is gamma, and delta, and epsilon. Say is equal to big F u v z zu zv. Then we transform. So then the original equation is a z x x plus b z x y plus c z y y is f x y z cx zy is transformed into alpha zuu, beta zuv, gamma zvv plus delta zu plus epsilon zv is equal to f uvz zu zv. Let's consider the hyperbolic case first. Hyperbolic case. P square minus 4ac is equal to 0. Let's consider the following quadratic equation. AR squared plus BR plus C is equal to 0 for some variable R. The discrimination equation B squared minus 4AC greater than 0 means R has two real solutions. Called mu and lambda. Such that lambda is defined as ux over uy, mu is defined as 3x over 3y. And these are called the characteristics of second order PDE. So then lambda is ux over uy is a solution, right? That means a over ux uy squared plus b ux over uy plus c is equal to 0. Or a ux squared plus b ux uy c uy squared is equal to 0. That means alpha is equal to 0, right? Likewise, mu is 3x over vy is also a solution. That means a 3x over vy squared b 3x over vy plus c is equal to 0, or a ux 3x squared b 3x 3y c 3y squared is equal to 0. That means gamma is equal to 0. Then hyperbolic type PDE becomes beta ZU3 is equal to F minus delta ZU minus epsilon Z3. It's simplified, right? Equation can be simplified. Form of PDE. Since u xy is constant, from this ux dx plus uy dy is equal to 0, or uy dy is minus ux dx, dy over dx is minus ux over uy is minus lambda. So one of the characteristics is dx dy plus lambda equal to 0. And likewise we can have dx dy plus mu is also equal to 0. So let's consider an example. For example, zxx plus xzxy minus 6x squared zyy is equal to x minus c to the x. So in this case, we have a equal to 1, b equal to x, c equal to minus 6x squared. The first step is find the characteristics. To find characteristics, so r squared plus x minus 6x squared is equal to 0. R plus 3x, r minus 2x equal to 0, or r1 equal to 2x. We say this is lambda. R2 is minus 3x. We say this is mu. So characteristics becomes dx dy plus 2x equal to 0, or y plus x squared is equal to 0. Actually, this is constant. Say this is u, xy. Dx dy minus 3x equal to 0. We have y plus minus 3 over 2x squared is constant. We say this is 3xy. Therefore, say u is y plus x squared, 3 is y minus 3x squared over 2, then zx is zu ux, z3 vx is zu ux is equal to 2x, z3 minus 3x is equal to 2x zu minus 3x z3. X minus inverse zx is actually 2 zu minus 3 z3. We are going to use this result later. Alpha is gamma is equal to 0. Beta is equal to 2ux 3x plus b, which is x, ux 3y, uy 3x, plus c, which 2c, 12x squared, 3y, uy, is equal to twice of 2x minus 3x, x times 2x minus 3x minus 12x squared is equal to minus 2 to 12x squared minus x squared minus 12x squared is minus 25x squared. Z delta auxx plus puxy plus c uyy is equal to a is equal to 1 times 2 is equal to 2. Epsilon avxx pvxy cvyy is minus 3. Therefore, we have minus 25x squared zuv plus EZU minus 3ZV is equal to x minus LZX is 2ZU minus 3ZV. And so this and this cancels each other. We have actually ZUV is equal to 0, or Z is some function of U and another function of V only. So we have phi y plus x squared plus psi y minus 3 over 2x squared. Now let's consider periodic type. B squared minus 4AC is equal to 0, or AR squared plus BR plus C is equal to 0, and you have a double root, lambda and lambda. And lambda is actually minus B over 2A, and dx dy plus lambda is equal to 0. This is a C1. For example, zxx minus 4xz xy plus 4x squared zyy is equal to 0. So A is equal to B1, B equal to minus 4x, C is equal to 4x squared. That means lambda minus 2x squared is equal to 0, and lambda is 2x. So dx dy plus 2x is equal to 0, over y plus x squared is constant. We set u is y plus x squared. How about v? The v is actually unknown function. So we can set arbitrary. We can set arbitrary function. Function for v. Obviously alpha is equal to 0, right? How about beta? Beta is 2ux 3x minus 4x ux 3y 3y uy 3x 4x squared uy 3y. So if we set 3 as x, and u we know that y plus x squared, so this is arbitrary. Then beta is twice of 2x minus 4x ux 3y 0. Just 1. 0 plus 1 and 0. How about gamma? Gamma is a vx squared plus b vx 3y plus c vy squared is equal to 1. Delta a uxx plus p uxy c uyy. This is 0, this is 0, this is 2, so this is 2. How about epsilon? Epsilon is avxx b vxy c vyy is equal to 0. So PD becomes z vv plus twice of z u is equal to 0. For this type of solution, we can try separation of variable. We can try the separation of variables. Such that Z is U type, V over V type only. Then Z V plus twice of ZU is U V double prime V twice of U prime U V is equal to 0. Or V over V double prime is equal to minus U over 2U prime, which is function of, this is function of V only, and this is function of U only. Therefore, it must be some constant. The left side is a function of V only, and the right side is a function of U only. So we say this is some k minus k. Then dv squared d square v plus kv is equal to 0, and du equal to k over 2u. So u is of the exponential 2 over ku type, and v can be sine root k v cosine root k v. The v z can be sum over k exponential ku over 2 c1k sine root k v c2k cosine root k v is over k exponential k over 2 y plus x squared c1k sine root kx plus c2k cosine root kx, and k will be determined by some condition, some boundary or initial condition. Actually, we can try the same approach for elliptic type. for elliptic, b squared minus 4ac is less than 0, or a r squared plus br plus c is equal to 0. We have two complex solutions, lambda plus minus I mu. That is dx dy plus lambda plus minus I mu is equal to 0. Or so for example, zxx plus y squared z yy plus yzy is equal to 0, a equal to 1, b equal to 0, c equal to y squared. Characteristics r squared y squared equal to 0. So dx dy plus I y squared is equal to no. R, since r squared plus y squared is 0, r is plus minus iy. So we say dx dy plus iy is equal to 0. Or ln y plus minus ix equal to 0. So we can say u is y exponential ix free y exponential minus ix. Or u is y cosine x free y sine x. We can say it this way. Then alpha is aux squared plus pux uy cuy squared is minus y sine x squared plus y squared cosine x squared is y squared. Beta is 2a ux free x plus 2c free y uy is twice of minus y cosine x y sine x plus 2y squared cosine x sine x equal to 0. Gamma is a free x squared b free x free y c free y squared y cosine x squared plus y squared sine x squared is y squared. Delta auxx plus puxy cuyy is, is minus y cosine x. Epsilon is a free xx p free xy plus c free yy is minus y sine x. Therefore the problem becomes y squared zuu c free v minus y cosine x cu minus y sine x z3 and zu is and plus y zy is equal to 0, and zy is zu uy, zv vy, zu cosine x, y cosine x, plus zv y sine x. So therefore we have the following equation: y squared cuu zvv is equal to 0. So again, you can try the separation of variable technique. So z is u over u, v over v, u square u, v square v, u equal to 0, or u over u double prime is equal to minus 3 over v double prime with just some k. So u double prime plus ku is equal to 0. V double prime minus kv is equal to 0. So from this we have sine root ku, cosine root ku. Here we have exponential root kv, exponential minus root kv. So the solution is then sum over k, c1k sine root ky cosine x plus c2k cosine root k y sine x, y cosine x, right, times d1k exponential root ky sine x plus d2k exponential minus root ky sine x. This is a general form of the solution. Okay, I would like to stop here today, and this is what we covers until the last class of today. And good luck with your finals. Thank you for your attention.